Okay, any questions about anything? I asked Alex, he said no, sorry. Were they in the case? Yeah, okay. So easy to pick up and take, yeah.
And I used to be able to track it if the case died.
Oh, I didn't know they had trackers. Okay, questions? You had a question, right? Yeah, I uploaded that, yeah. Sorry about that delay on that. I was going to upload it Friday, but didn't make it to the office. And the internet basically sucked over the weekend. You know, I don't know if you guys had that problem too. Yeah. Question?
Are there going to be set office hours, or are they just going to sort of be random each week?
I'm hoping that like I want to get this more organized, and the TAs are working on their Slack space. I've been watching this, you know, going on, and I know that they're covering them this week, and I'm thinking, like, one person said, oh, I can do Friday every week. So I think he's going to be locked in on Friday. And for the other days, I'm assuming that someone's going to be the steady person there. But they will happen. It's a question of, is it going to be the same TA every time? That's what I'm waiting to find out. Yeah?
Will there be office hours held this week prior to like the homework?
Yeah, yeah. Yeah, like today. The thing that here's something that's come up though. You know, the College of Engineering was generous enough to offer classrooms for office hours because of our uncomfortable room up 429 Phillips. I don't know if you've ever been up there. It's kind of like a, you know, it's kind of like the attic from the picture of Dorian Gray. You're worried that if you go in there, you're never gonna leave. So they gave us classrooms. Awesome. They gave us, you know, classroom in Thurston on Fridays. They gave us classroom in Hollister Monday, Tuesday, Wednesdays, you know, in the early evening. And so the TA went there last week to the one in Hollister, and the door was locked, and it had a key card access, and he couldn't get in. Okay, so he trucked everybody over to Phillips and did it in 314 or something. So I got in touch with the authorities through Charlene, and there's this guy who runs Hollister, and I said, okay, do they have to request card access? And he said, yes. And so I figured that would be easy. So I told all the TAs, file a card access request with me as the advisor, and I'll sign off on it. Well, it turns out Hollister is not an option in the card access request. So last night I sent an email to the building guy again, asking, you know, you've been getting these emails, right? Yeah, like, you know, dude, how do they get card access?
I think what happened last week was the battery on the lock ran out, and it automatically locked itself.
It locked itself.
When it saw that, so like card access wouldn't have helped at 7 or...
It wouldn't have helped last week, but it would help this week because presumably they fixed the battery.
Yeah, but the doors are supposed to stay unlocked until 9 apparently.
Oh, really? I thought it was just the building stayed unlocked until, okay, yeah, all right. Well, maybe they'll be unlocked. So go to Hollister today if you want and see if the TA can get in, you know, or if they're still playing this trick on us, you know, that we can't use the room. But anyway, so yeah, the answer, that's a long answer to your question, which really translates to yes. Okay.
We could always check out Bard 140 if 306 Hollister. I mean, that's sometimes been.
But that's more of a like a stagey kind of room, you know. It's not like.
It's not collaboration space.
Right. No.
Make it.
Yeah. I've taught classes in that room before. Anyway, other questions about anything? Alrighty, so last time, very important result. This whole Fourier series thing. So Fourier series for periodic signals. Say a periodic signal x of t, whose fundamental period is, say, t0. Fundamental frequency f0 equals 1 over t0. And it looks like this. And we're talking the complex exponential Fourier series because everything's so much cleaner when you do it that way. X of t equals whatever that means. Sum from k equals minus infinity to infinity, ak e to the j k 2 pi f0t. And the coefficients ak are given by a neat formula. I separate out the a0 one because I want to illustrate exactly what it is. 1 over t0 integral sub t0. I'll remind you what that means in a sec. X of t dt. And for the other AKs, AK equals 1 over t0 integral sub t0 x of t e to the minus j k 2 pi f0 t dt when k is not equal to 0. And this notation, integral sub t0, means, quote, integral over any interval of length t0. Now, last time I reminded you, that we already had Fourier series for a restricted class of signals, the ones that were a finite sum of sinusoids with harmonically related fundamental frequencies. For those, you could just play around and reindex and whatever, use Euler, and get the Fourier series without doing any integration at all. So I don't want you to be worrying about doing integration for those. But for things like square waves and triangle waves, whatever, you're presented x of t as a function of t, explicit function of t, or maybe a graph. And doing these integrals is the way you find the AKs. And at the end of the class last time, we were talking about what the convergence properties of these things. And I want to finish that up. But before I do that, I want to give you a piece of terminology that the book uses and that we're going to use, and it comes up later as well when we talk about discrete time Fourier transforms and all that kind of stuff. So here's terminology. Let's call this equation star, and let's call this pair of equations double star, just so I can refer back to them. Equation star is what people call the synthesis equation. And why do they call it that? They call it that because you're synthesizing x of t as a sum of pure sinusoids. And double star, the equations for the Fourier coefficients, people call the analysis equations. And essentially what you're doing there is you're analyzing, quote unquote, and analyzing, if you think of as sort of pulling apart and looking under the hood and whatever, x of t into components, into pure sinusoidal components. Okay, so we have our analysis and our synthesis equations associated with Fourier series. And we talked about convergence. And I won't repeat what I said last time but on the board, but what was it? X of t, for this even to work, has to be reasonable. Okay? And reasonableness means it's, it has only jumps as discontinuities, only finitely many jumps for in every period, and no cusps, all that kind of stuff, the Dirichlet conditions. And under those conditions, this infinite series always converges. It converges for all t. What does it converge to? Well, if t is not a jump, it converges to x of t. If t is a jump, it converges to halfway across the jump. Nice kind of convergence. But at the jump, it turns out to have interesting behavior. And I mentioned that last time, and some people had seen it in their courses where they saw Fourier series and maybe in physics classes. But at a jump, recall that the series converges to the mean value across the jump. Okay, now near that jump, how do the terms behave as the number of terms increases? So how does the series behave near that jump? And it doesn't matter what kind of jump, what kind of signal you're considering, but the simplest example would be to have like a square wave, where you have just a flat thing, jump, flat thing, jump, flat thing. so near that jump. So let's look at a square wave. And I'll try to draw some pictures. This is one time when it would be cool to have like a nice animation to show you, but unfortunately I don't have that with me today. Say you got this. This is your signal, x of t. And I want to look at what's happening right at this jump. And when you draw a picture like this, where you go across and then you go down and then you go across, it's not like there's anything happening here except a jump. Really, if you wanted to be rigorous, you would put like a dot somewhere, like a dot here and an open circle here. But this is the way everybody draws it, just to make it clear that you're talking about a square wave. OK, so say this is 0. And yeah, it doesn't matter what the time is. So let's say this is, let's do that. How about that? All right. So what happens near this jump? Well, if you do the first few terms of the Fourier series, the first term is just going to be 0, or the 0th term, so to speak, is going to be 0, because it has 0 mean. The 0 plus 1th term, the first harmonic, remember we had that terminology from the last time of this thing, and we're going to talk more about that later, is going to be a pure sinusoid, and it's going to look something like this. Okay, so that's the first order approximation of this square wave, so to speak. The closest sinusoid, pure sine wave to that square wave. What about when you add the next couple terms? What does it look like? Let's draw this a little bit. It's going to look something like this. And I have to do the top one first for some reason. I don't know, I have this problem with that. Oh. It's going to look something like that. OK. Now, that's a little better approximation to the square wave than the pure sinusoid. And you can see there's this little overshoot, and then there's some undershoot in here. But these, where it's getting closer and closer to the edge there. And if you add the next few terms, keep going and going and going, it always ends up looking like this. So after lots of terms, your approximation near that jump is going to look like this. That's not good. OK. It's going to go up, and it's going to go down, like so. OK, so I'm being really schematic here, really rough. Same thing is going to be going on down here. All right. So what's going on here? You can see that the sum of the terms, which is the squiggly things, that's converging onto the flat parts of the square wave at t in the flat parts. At the jumps, it turns out with the square wave, it's always equal to 0, so it trivially converges to the mean value across the jump. But what happens near the edges? Well, as term number increases, the width of like the area around the first peak that's near the edge shrinks, and it moves closer and closer to the jump value. But the height of the first peak always remains 1.09 roughly times the height across the jump. Okay, that's a weird thing that happens with these things. So as number of terms increases, the ripples collapse in on the flat parts of x of t, and the width of the quote-unquote first ripples before and after jumps shrinks to 0. But the height of that thing is always going to be about 1.09 times the value across the jump. So the height of the quote-unquote first ripples is always going to be roughly 1.09 times the jump distance. I'll put that in quotes. And this fact here, this is known as the Gibbs phenomenon. And this is a classic thing that happens with Fourier series, and it turns out to bedevil a lot of digital filter design algorithms. You have to get around the Gibbs phenomenon somehow. It's something you can't do anything about. Question? Yep.
So not, excuse me, I don't know what else to call it, but like the first term.
Yeah.
Would that peak be 1.09 times the average value?
You know, that's a really excellent question. I've never tried to figure it out.
Is it just asymptotic, where it kind of approaches 1.09?
Yeah. It's always roughly 1.9 asymptotically, but you know, that's a really good question. You know, and I could easily figure out the answer to that by just doing the math. Maybe are you able to do the math in your head, Alex? No. Okay. So I'll check that out after class, but that's an excellent question. Because this is the first jump, right? Yeah. So anyway, I think it's more asymptotic, but you know, we can check it out.
Thank you.
Yeah. All right. So the Gibbs phenomenon happens a lot. And if you ever wondered who Gibbs was a professor at Yale, a math professor at Yale, and people call him the first American mathematician. Okay, so what does that mean? Well, clearly there's plenty of like 10-year-old kids who are mathematicians back in the Revolutionary War era and whatever, but Gibbs was the first American who like became a published, renowned mathematician, and so that's why they call him the first American mathematician. And he also worked in thermodynamics as well. Has anyone ever taken a thermo class like ME 22 whatever? So you heard of Gibbs free energy? Yeah, that's after Gibbs, same dude. Okay, so anyway, Gibbs, first American mathematician. Do we have anyone named Gibbs in the class? Yeah, one year we had an Angus Gibbs, and so every time we talked about the Gibbs phenomenon, we could point to him. Anyway, okay, so that's another thing about convergence, this analysis and this synthesis equation terminology. Okay, so now we're going to have a little bit of, I hope, fun, talking about like music and stuff, and so we have the stage prop from the lab. We have this keyboard here, and talk about that. But before that, I just want to pause, and I want to. This is one of those cognitive science questions that's always intrigued me, and I just want to. I always ask the class, do you think I'm making a mountain out of a molehill here, or is there something serious about this? Okay, so what does the Fourier series do? It divides up the world in terms of frequency, in some sense. It divides up the periodic signal world in terms of frequency. Okay. Now, ECEs. What do they talk about? Well, we talk about things like, we call people, we name people's specialties sometimes as a matter of frequency. Like if we talk about Ehsan Afshari, who's a faculty member here who left for Michigan a few years ago, what do we call him? We call him a terahertz guy because he does terahertz circuits. And we call this other person a microwave engineer, right? Because they deal with circuits and whatever systems that process microwave frequency signals. The point is, we think about spectra and frequencies and all this kind of stuff. We divide up the world that way for some reason. All right. Now, one could say that humans evolved, all right, to find simple answers to complicated questions, right? Because here's why. Here's why, okay? If you're a caveman or cave person, whatever, anyway, I don't know what pronoun the cave people used, but whatever. If you're a caveman and you know you hear like the roar of a lion outside of your cave, right? All right. What's the simple answer? Simple answer is that's a lion, and I better slide the boulder. That's a simple answer, okay? The complicated answer is, oh, that's Barney Rubble dressed up as a lion. Kidding me, I'm going to go out and, you know, mess with him. Okay, who wins the Darwin Award? Okay, who survived to give offspring? The person who came up with a simple answer. It is actually a lion, right? All right, so bottom line, humans finding simple answers to questions in the real world helps people live and helps people reproduce. And so we ought to be compelled evolutionarily to find simple answers to things. And what could be more simple than a pure sine wave, you know, like that? That's one kind of just so story about why do we come up with Fourier series? Why do we divide up the world in terms of frequencies? It gives us a simple way of, you know, whatever. But on the other hand, it could be that we are compelled evolutionarily by our anatomy to divide up the world in terms of frequency. Why? Well, if you look inside a human ear, what do you find? Well, you probably learned all this when you were in grade school. You know, there's the eardrum, you know, don't put a Q-tip in, whatever. Then there's the middle ear, you know, semicircular canals, balance, whatever, that kind of thing. And inside, deep inside is the inner ear. And the main character in the inner ear is this thing called the cochlea. And it looks kind of like a Nautilus shell, right? It's kind of a, well, what happens? What does the cochlea do? Well, if you unwind the cochlea, saying cochlea is like people who say nuclear. Anyway, don't even get me going on that one. But if you unwind the cochlea, what do you find? You find inside the cochlea, you find hairs, hair-like structures. And they're of different thicknesses. And they vibrate, they resonate according to frequency. In a sense, so what compels us, here's the question, to, and I'll put that word in quotes because I know I certainly object to people telling me I'm compelled to do things, but I think we are sort of compelled to divide the world up in terms of frequency, divide the world of signals in terms of frequencies. Well, one possible answer is the anatomy / physiology. And anatomy just means the way things are put together. Physiology means the way they work, okay, of the cochlea in the inner ear. That what it is, it's essentially, when unwrapped, a spectrum analyzer. And what happens is when sounds go into your ear, if you were able to unwrap the cochlea and see what's going on, then the frequencies of the sounds make the hairs vibrate according to the thicknesses of the hairs. Like the low frequency sounds make the thick hairs vibrate, the high frequency sounds make the thin hairs vibrate. And they're all lined up in decreasing order of thickness, just like an F space. So it looks just like, quote unquote, F space with thicker hairs, thicker vibrating hairs, I'll put in quotes because it's really just hair-like structure. To the left, the low frequencies for low frequencies, thinner for high, etc. All right, so on the one hand, we might have been compelled to find Fourier series because we want to find the simple answers to complicated questions because that helps us reproduce. On the other hand, maybe our anatomy is nudging us sort of resolutely and irrevocably in the direction of thinking about the world in terms of frequency. There's plenty of other ways to divide up the world of signals. You know, there's wavelets, there's all kinds of things, but we do it this way. And we divide up our engineering in that way. So, you know, I don't know. Is this interesting? To me, it is. Like, why do I call that person a microwave guy? Or, you know. Anyway. All right. So, a good venue, like I said, for thinking about these frequency and periodic signals is music. Okay. So, a sort of a what's a good word here? I'm stuck on compel. I think compelling. No, get that out of my head. So a nice, I don't know, venue for thinking about things like periodic signals, frequency, etc., is music. Okay, so why is this a nice venue of thinking about these things? Well, you have these kind of rough correspondences. Okay, so you have rough correspondences. One of them is going to be a periodic signal. And this is going to be a periodic auditory signal, periodic audio signal. That corresponds roughly to a musical note. Now, here's another thing that I always wondered about. This is one of those, like, did you ever notice that the word note and the word tone are anagrams of each other? Coincidence? You know, ancient astronauts? You know, what made this happen? I don't know. Pitch is going to correspond to fundamental frequency. Like so. So those are rough correspondences that we can draw between periodic audio signals and musical notes and fundamental frequency and pitch. Okay? And how many people have never ever played a musical instrument before, of any kind? Okay, good. It would be okay if there were such people, like the CU AUV guy I mentioned a couple lectures ago that I know from a few years ago. Not you, but he took it in spring of 2015. He proudly said he had never ever played a musical instrument in his life. He knew nothing about music except, you know, to listen to things. And then on the other end of the extreme, we have Alex, who our TA and videographer, who has perfect pitch, which means that if you play a note, he can tell you what note it is. So what do I mean by what note? What do I mean by that? Okay. Western music, and that's a culturally freighted term. Okay. So Western music, at least nowadays, is based on what we call this equally tempered tuning system. All right, so to illustrate the equally tempered tuning system, I brought this keyboard today. All right, so anyway, here's this keyboard. This is a cheapo Yamaha, whatever, you know. I got it from some guy on Lake Street when he was moving out of Ithaca. But anyway, you could see this is a piano keyboard, okay? That's how it looks to the person playing the keyboard. And these notes have names. Like, for example, this one is called a C, and this one's called an A. Why? You know, I don't know, history, whatever. Okay, but what does equally tempered mean? Well, we're going to think about what that means in terms of this keyboard. All right. So Are we good? All right.
We only lost a little bit. We'll edit the plug noises.
Don't have to edit anything. It's part of the entertainment value of the lecture if there's you know, tech mistakes that happen. You know, it's always fun, like when I was a TA, I learned out how much fun it was to like call out the professor on, you know, stupid stuff they did and make, you know, undo the damage and whatever. But anyway. All right, so it's based on an equally tempered tuning system. Here's some terminology. Terminology is that if you have a note whose pitch is F0, fundamental frequency F0, and one whose fundamental frequency is 2F0, so we call two notes with fundamental frequencies say F0 and 2F0, we call those notes, quote unquote, 1 octave apart. What is 1 octave apart? You can also say that the 2F0 note is 1 octave above the F0 note, and vice versa. The F0 note is 1 octave below the 2F0 note. Why do they call it an octave? Well, if you look at the keyboard, again, look at the keyboard. I hope everyone can see. You'll discover, like I told you that this is a C, and the next C is this. And it turns out that these two adjacent Cs on the keyboard, their fundamental frequencies are 1 octave apart. This one has some frequency, and this one's going to have twice that frequency. And if you count the number of white keys to get from this one to this one, you find out it's 8. You know, it's like 1, 2, 3, 4, 5, 6, 7, but 8 when you start on that. So that's why they call it an octave, because it's 8 white keys in between notes that are an octave apart, that are white keys. And of course, they're black keys. We don't worry about that for a second. OK, so the reason for the terminology, the oct terminology, comes from standard piano keyboard. Now, if you listen to notes that are an octave apart, they have a kind of a similar sound to them. So let's see. Let's find an outlet that this fits into. Great. I know there's one over here, but I don't want to be tripping over that. No. Let's see. Yeah, you know, this kind of outlet that's under one of these doors, my Mac power thing doesn't fit in there. So you go to a conference room for a meeting, and you want to plug in your computer, and you didn't bring the long cord. You just brought the little cube. No, you can't plug it in. Same here. You can't plug in the keyboard. So maybe during the break, I'll go and borrow an extension cord from somebody. All right, here's the power. And let's make sure this. Where's the power? No, there's a. Where is it? I'm not used to looking at it this way. Huh. I thought it was with the volume thing, but it isn't.
Would it be the big red button?
Big red button? No.
Or the one to the left of the volume?
There we go. It's this button, this little red button. OK, there we go. All right, so I don't know what this is set on, but I'm going to play you a C. Let's turn it up. Now I'm going to play you the next up C. Now see, there's something about those notes that, like, they sound, you know, and the next up C, Those are all Cs. They're all respectively a factor of 2 apart in frequency. Okay. So that's what octave means, a factor of 2 in frequency. Now the next step, sorry about this, guys, but I mean that's the way it goes when you have a bad outlet in the table. Next step in the Western tuning system. I'll put Western in quotes because that, like I said, that's freighted. That's culturally ethnocentric. Yes?
So when you say like, so the first C is like F0, the second C is 2F0, is the third C 4F0?
Yes. 0, 2, 4. Good point. Keep that, hold that thought, okay? Because what happens next? To tune let's just keep it fixed, a piano. What they do is they pin down the frequency of one of the notes. So you first pin down the frequency of one particular note. And the note is, I'm going to tell you a couple of names for it. A above middle C. And this is also known as A4. And I'll explain why it's known as A4 in a second. To 440 hertz. And when I'm talking about the frequency here, I mean the fundamental frequency. All right, so on the keyboard, what is, and see, the reason it's good to, one of the reasons it's good to have Alex's perfect pitch in the room is he can tell me whether this thing is in tune or not. Okay, so this is middle C. Does that sound right?
Close enough.
Close enough, okay. This is the A above middle C. Fundamental frequency of that note is 440 hertz. Okay, you pin that one down. Then what do? You pin down all the other A's by this octave relationship. So what does that mean? That means once you've got the A above middle C, that's a 440 hertz. You go an octave down, that's 220. It's 110. You know, this is 880 hertz. This is 1760 hertz. It doubles every time. Okay? It doesn't just add 440. So now you've got all the A's tuned. And finally, you tune all the notes in between the A's as follows. So tune all the notes, including the black keys, between the A's. Let's see, I must try to step over it this time instead of. What does the last word there say? Can anyone read it? Yeah, as follows. Okay, so you start with an A. The next note up has frequency 2 to the 1/12. That is to say, the 12th root of 2 times the frequency of the current note. Okay, so you start this algorithm off with current note equals some A. And you tune the notes up to the next A because it turns out there's 12 notes, 12 steps, 12 what they call half steps in music between A to the next up A. Each one of those is going to be 2 to the 1/12 times the frequency of the current note, and that gets you to 2. when you get to the next day. So this is nice. This works because it gets you to 2 times the current A when you get to next day. Now that's what's called the equally tempered tuning system. All right. So first observation about the equally tempered tuning system is, mathematically speaking, like how is the keyboard arranged? Like you go up the keyboard and you put a number on each note for corresponding to its fundamental frequency. How is mathematically speaking, how would you characterize the way the keyboard is laid out? What kind of a scale is it laid out on? No pun intended. Scale. Any suggestions?
Harmonic.
Sorry?
Harmonic.
That's a good word, harmonic. It's a very good word, but it's not what I was looking for. How about this? I'm getting tired. Sorry? I heard it. Yes, it's laid out in a log frequency scale. If you move a certain distance across the keyboard, then that's going to be this for each, like if you move 12 notes, a distance of 12 linearly, that's going to double the frequency. You know, that kind of thing. So this is, the keyboard is laid out in a log frequency scale when you think about it. So that's a good thing to know. You can, like, that's a cool thing to bring up to people who just know about music and they've never had a signals class. You know, you just sort of say, did you know that the keyboard is laid out on a log frequency scale? And they'll say, what does that mean? And you'll explain it to them. And here's a little piece of fun history to go along with this. Notice a 12th root of 2 is not a rational number, right? It's not a rational number. And so the question is, you know, is there some way to lay the frequency out on a log frequency scale somehow, or roughly speaking, so that the ratios between the frequencies of any 2 notes are rational numbers? And you may wonder, why would anyone ever want to do that? Well, it turns out there was this guy named Pythagoras. You've all heard of Pythagoras, right? Pythagorean theorem. And he was a Greek mathematician. He was from one of the islands in the Mediterranean. I forget which one. But he sort of had this cult of people who followed him. And the cult, I'm totally serious about this, the cult was about rational numbers. That everything in the world is rational, that everything good is rational, and everything bad is irrational, and all that stuff. And so back then, they didn't have pianos. They had, you know, lyres, you know, stringed instruments, right? And they said, OK, well, maybe we can make it so that all the notes that sound nice together have rational ratios between each other. So, like, if I take a string of a certain length and pluck it and I get a certain note, and then I turn the string into 3 halves that long, I should get a related note. OK? And they tried to fix it so that all the things were rational, and it turned out they couldn't do that, and it was a struggle. Like it turns out that these 2 notes, no, these 2, are roughly 3 halves. This is roughly 3 halves times this, frequency-wise. It turns it. You nod your head as if you can sort of tell that. That's pretty cool. I wouldn't know, but that's what's called in music. That's called a fifth. Like, it's called a fifth because there's 5. You take 5 steps to get from one white key to the next one. The particular one I typed was C and a G, but it's not quite 3 halves. It's actually 2 to the 7/12ths. Okay, because you take 7 steps to get from the C to the G, and each step is a ratio of 2 to the 1/12. So anyway, Pythagoras, then we're going to take the 3-minute break, and during the break, if you want, I'll tell the punchline of this story is Pythagoras allegedly, they were on a ship, him and the cult, right? And one of the members of the cult, you can look this up. It's actually, there's a Wikipedia page that describes this urban legend, or I don't know whether it be urban, whatever, Athenian legend. that some guy, one of Pythagoras' cult members, was downstairs in the ship, and he discovered a neat proof that the square root of 2 is irrational, that you can't write it as a ratio of 2 whole numbers. And the cult had been struggling for years to prove that square root of 2 was rational, because square root of 2 is obviously, you draw a triangle that has sides 1 and 1. This number we know by the Pythagorean theorem is square root of 2. That's got to be a rational number, right? Because it's such a simple picture. But this guy proved that it was not a rational number. And so what do you think happened?
Well, he got thrown off.
He got thrown off the boat. Yes, he was thrown overboard. OK. So well, let's take the 3-minute break. And if anyone wants to see a 2-line proof that square root of 2 is irrational, I'm happy to do it during the break or after class. So. And then we'll do some more with the keyboard. This correspondence between frequency, fundamental frequency and pitch, periodic signals, musical tones, musical notes, whatever you want to call them, octaves, equally tempered tuning systems, and so on. And so that's good. And we see where the equally tempered tuning system comes from, etc. And no one asked for the 1-line proof that square root of 2 is irrational. I'm not offended, but I'll.
Oh wait, could we see it?
No, after class, if you want to see. No, I'm not going to waste class time on. No, just kidding. All right. So anyway, what does an A440 sound like? I already played it for you, and now Alex tells me this I learned 2 years ago, or a year and a half ago, that at home I have sheet music for, and we'll talk about what sheet music is. I have a sheet music for this song, right? You've heard that one before, right? Now, my sheet music is in A major, okay? Alex claims that the version the band plays is in A flat. Is that correct, band people? There were people who raised their hand last time that were in band. So instead of being, it would be something like this. Like that. It would start out 1 flat note down, right? Okay. So no band people can back me up. So I'm supposed to believe you.
Well, it's true though, because at least when they went to see you downtown, right? When they played it, it wasn't A flat.
Oh, well, see you downtown rules then, right? That's the canonical representation of the alma mater.
Actually, the canonical representation, so there's this arrangement of a bunch of Cornell wind songs called Songs of Cornell.
Right.
And in the original score, it's for band, so it has the alma mater, 6 or 7 fight songs. So I think for wind band, that's the definitive reference for what key all the songs should be.
Okay, and that one says A flat.
Yes.
All right, fair enough. Well, I learned it in A. I'm not going to try to learn it in A flat, All right, but when you hear someone play the alma mater, they don't just play this. Unless they're a 1-note instrument player. If they're a piano player, they play something more like this. Something like that, right? No. I could do the Harvard fight song too, by the way. No. What's that? No. You recognize that, right? 10,000. No. 10,000 men of Harvard want victory today. Blah, 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 blah. It's all about how much they hate Yale. Okay. Yeah, Cornell, it's a bummer because we hate Harvard, right, hockey-wise, and said, if you go to a hockey game, you'll hear this. Let's see. Let's see. Anyway, I can't do it. Oh, Canada. I need a pedal for that. Okay, so anyway, Harvard, we hate Harvard and hockey, but they don't hate us as much as we hate them. They hate Yale, so it's almost like insulting that we're not hated back equally by Harvard. They don't consider us the arch rival that we consider them. All right. Anyway, but like I was saying, you don't just hear a melody like this. You hear more notes, right? And so, how do these notes? How do people know what notes to play other than they're very talented and they just figure it out by ear? Well, they have this thing called sheet music, right? And you've all seen sheet music, what it kind of looks like. It looks like this. So what is sheet music? I would call it, in the context of this class, it's a signal medium, okay? It's like the ether or a wire, okay, or whatever. But it's a signal medium for intergenerational transmission of music, okay? So that's essentially a signal medium, like a wire or whatever, for intergenerational. And I'm using that word in a super broad sense, just to mean like from point A to point B without any kind of auditory connection or temporal connection or spatial connection. Transmission of music, musical signals. Okay? And like you could have your typical sheet music, like, for example, the beginning of the alma mater would look something like this. You would have like something like this, and then you have one of these, and then in my version you would have this, this, and this, and then you would have like this note and this note, like so. That's the from far above Cayuga's waters. That's like this. Okay. No, this. Right, Alex? Yep. Okay. Anyway, and they're probably quarter notes in my edition, so I'll put that. And then there's more. There's more notes like that. Now, what does this indicate? This indicates that when we hear a piece of music, we don't actually hear periodic signals. We hear finite duration versions of an A440, finite duration versions of a C sharp in this case. These things, by the way, just tell you that every time you see a C, you're supposed to play C sharp, and this happens to be a C, whatever. Okay, but in any event, the sheet music shows you what to play, but when you play / hear something like this, you don't hear actual periodic signals, because periodic signals go on forever. Those go on forever. And it would be a pretty boring piece of music to just be like A440 forever, right? Now that's probably the second most boring piece of music I can think of. The first most boring piece of music I can think of is a famous piece by John Cage. Anyone ever heard of John Cage? Avant-garde composer. I think it's called 5 minutes 44 seconds.
That's 433.
433. I knew it was an arithmetic progression from number of minutes to number of seconds, and it was a palindromic number of seconds, but I couldn't remember whether it was 544 or 433. So there's a piece called 4 minutes and 33 seconds. Have you heard of that one? Where the performer just comes in and sits down and doesn't do anything for exactly 4 minutes and 33 seconds and then bows. That's the way it goes. Okay. Now, one could plagiarize that and just play A440 for 4 minutes and 33 seconds. And say, that's my variation on a theme by John Cage, right? Something like that. But the bottom line is you don't hear periodic signals. You hear pieces of periodic signals. You hear like a C and an A for a little while. Or maybe if it's a one-note player, you just hear A, B, C sharp, da 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 da, like so, right? So that's what you're hearing. But still, you think of frequency when you hear these things. You think, oh, I'm hearing an A. Oh, I'm hearing a C sharp, even though I'm only hearing an A for a while. Okay, so despite the sort of the finite duration nature of the sort of the A's and C sharps, etc., that you hear, you interpret them in terms of their frequencies, their pitches. As if they were actual periodic notes. All right, so we want to get a grip on understanding the frequency content of signals that aren't periodic, but for which frequency content makes sense in some sense. To me, it makes total sense that this that sounds like an A and a C sharp for a while, then it sounds like a D and a B, and then it sounds like a C sharp and an E for a while. I'm using these names for the notes even though they're not forever periodic signals. Their pitches are just going on for a while. But the bottom line is that we want to make sense, sort of make some kind of sense of sort of frequency content, quote unquote, for situations like this, where the idea of frequency content, and I'm going to unplug this for the moment because I know I'm going to trip over it. So like this, where quote unquote frequency content makes sense in some sense. And we know how to do this when you have a superposition of pure sinusoids that go on forever. So far, we've only addressed at frequency content. And we've done this by means of the spectra of these signals of actual superposition. Well, let's put the actual later. Sums of true, quote unquote, forever sinusoids. Okay, so what do we do when you don't have a situation like this, but when you have something going on like you have when you're playing a piece of music, where you have a note that's being played for a while, and then another note that's being played for a while, or a bunch of notes that are played at the same time? It's like a chord. How do you make sense of the frequency content? Well, it turns out that the sheet music is a rudimentary example of what people call a time frequency plot, time-frequency plot. So the sheet music is a rudimentary example of what people call a time frequency plot for the musical signal represented by the sheet music. Okay? So if I see what in the sheet music, you're going to have not only things like notes of this kind, you're going to have little indications about like how long they go. So this is going to be shorter than this one. And the shortness is indicated by the dots here. So like I would have far above. The is shorter than far, that kind of thing. It tells you it has essentially frequency on the up and down axis because the pitches are indicated by the points in the musical staff, and it has time on the horizontal axis. So the quote-unquote vertical axis is frequency, which is embodied, in the case of music, by pitch. And the horizontal axis in sheet music is time. And the symbols indicate that you're going to have such and such frequency content, such and such a note being played for so and so long, starting at thus and such. I don't know, how many different ways of saying so and so can you think of? Time. So it tells you, the symbols tell you what frequencies, starting when, and for how long. And that picture over there tells me that I play these two frequencies, the frequency corresponding to a C sharp and the frequency corresponding to an A. And then I play these two, the one for a D and a B, for 2/3 as long as I played those, starting at the end of playing that, that kind of thing. All right, so sheet music is like a time frequency plot. And a more sophisticated way of doing time frequency plots for arbitrary signals that aren't things like melodies and chords that are more complicated, this is something we're going to be spending some time on later in the class, but you're going to see in the first lab, the first actual lab, is this idea of a spectrogram. Okay, so these think always when you think about spectrograms, and we're going to talk about these in more depth later during the semester, but you're going to see them, you're going to get a taste of them in this first lab, are another example, a more sort of sophisticated example of one of these time frequency plots. Essentially, you have frequency on the vertical axis. So this is freak. And essentially, you have time down here. And you have like a grayscale image up here. And it looks, like this. You're going to have stuff like that. And maybe this one, you're going to have whatever. What does this mean? This is going to mean like in this little space of time, these two frequencies are happening, and however dark the grayscale is, that's how loud those frequencies are happening. That's the strength of those frequencies in the signal. And there might be overlaps, all that kind of stuff. And there's all kinds of user choices associated with the spectrograms, like the window length and the FFT length and all that. Later on in the class, we'll talk about that. But in my opinion, a good way to think about spectrograms is sheet music. It's just like whatever. Sheet music is a spectrogram, in a sense, for this musical piece. And it has the same axis orientation and everything. And in the book, there's, I think it's page 81, if I recall, of this edition. There's like a sample of sheet music, okay? And anybody who's ever had piano lessons can look at that and tell me immediately what it is, what song it is. So does anyone happen to have the book with them today? Alex, you have your e-reader. So find someone who's had piano lessons and see if she or he can identify that piece of music on the bottom of page 81. Yeah, I think it's page 81. It's something one. All right. And I'll play the first few notes of it on the keyboard if you want to hear it. OK, so far, actually, if you think about this, last time we talked about Fourier series. We took a signal of periodic signal, fundamental frequency f0, expanded it in a Fourier series. Here, this whole discussion of music, this whole discussion of auditory signals, the frequency is pitch, blah, 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 we haven't talked about anything to do with the higher harmonic components of periodic signals, about the Fourier makeup of the signals and what that has to do with the way that the notes sound. We've only talked about the fundamental frequency. So let me close today by talking about that. All right, so far the music discussion so far has only talked about this sort of note, this fundamental pitch of a note corresponding to fundamental frequency of a periodic signal. Okay? And a periodic signal has more to it than just its fundamental component. So a periodic signal with, say, fundamental frequency f0 has not only what we called a fundamental component, but also higher harmonic components. And now you see why this word, this H word that you brought up earlier over there, like when we were talking about higher harmonic components, why we use that kind of musical sounding word in Fourier series, because we're drawing this connection between periodic signals and musical notes, musical tones. So what does this all have to do with music? Well, okay, A440, I've been playing it on this keyboard, right? And it's been doing the piano sound, right? So let's see if this is an A440. But if I'm on stage, right, and I want to play like my square wave synth, right? That is preset number 88. Is that an 88 or 89? I can't read it. 89. Okay, so what do we do? That's a square wave, okay? And you do the alma mater, that sounds different, right? But that's the same note. It's an A440. It's the same note. Same note, but come on. It doesn't sound the same as that. So different A440s on different instruments, like, what instruments have A440s? I think an oboe probably does. Anybody play an oboe? Viola does. I learned that last semester from Patrick, our viola player. I forget, what instrument do you play, Alex?
All of them.
All of them, okay.
Primarily bass trombone. Bass trombone has an A440.
It does? It's one of its highest notes? Yeah. Okay. Well, yeah, anyway, A440s. A440, same note, different instruments. And the difference in sound between A440 played on different instruments is a difference in what a musical analyst might call the timbre, which is actually a word that covers a lot more than harmonic components. It covers things like, attack, decay, breathiness, whatever. But the difference in timbre, or sort of how they sound, quote unquote, sound quality, reflects, among other things, the difference between the higher harmonic components in their Fourier series. How the energy in the signal is splayed out over frequency, over harmonics. Okay. So how I would say the signal energy is distributed over the various harmonic components. And we saw last time when we looked at the square wave that the Fourier series coefficients died off relatively slowly as k goes to plus or minus infinity. It died off like 1 over k. And it turns out that harsher sounding notes tend to have Fourier series that decay slower as k goes to infinity. Mellower sounding notes, the coefficients decay faster. And that's an auditory manifestation of what I was talking about. Spiky signals, signals have jumps, rapid variations, versus signals like a triangle that are continuous. You know, that's an auditory manifestation of that. So roughly speaking, so lots of higher harmonic energy corresponds with harsher or sharper sound to the note. And if you want to think of an example, just think of that square wave that we just had versus the piano sound. Okay. And that's why we call them higher harmonics and whatever. And let's see, do I want to talk about anything else today? Like start at something new? I don't think so. So let's wrap that up for today. And then next time, we're going to start talking about sampling. And that'll be fun.